So chemistry involves measurements and calculations. In this chapter, we're going to learn some rules for reporting our measurements and calculations. And once we learn these rules, we're going to apply these rules and terms for the remaining of the semester. Um, so oftentimes in chemistry, when we do measurement, we need to report numbers that are extremely big or small. One way to write the numbers that are either too big or too small is writing them in scientific notations. Scientific notation consists of two parts, two components. First is the numerical value, that is between 1 to 10, and then it's times 10 raised to some power. So let's look at some examples and see how we can write numbers in scientific notations. So let's say we want to write this number 0.000423 in scientific notations. So in order to write this in scientific notation, first step is to put the decimal right after the first non-zero digit. So 4.23 times 10. Now, we gotta find out what the power of 10 is here. So two ways we can do this. First of all, you want to count and see how many decimal places you move the decimal. So 1, 2, 3, 4. Now the question is it -4 or +4? So two ways you can tell if it is a -4 or +4. First of all, if you're moving the decimal to the right, the sign is going to be -4. The other way of looking at this is that 4.23 times 10 to the 4th. Now here, the original number, which is 0.00423, is a very small number. By moving the decimal right after 2, you're making a number bigger. So to compensate for that, this has to be negative. Now let's look at another example. You want to write this number 353000 in scientific notations. To write this in scientific notation, you first want to put the decimal right after the first non-zero digit times 10. Now, in order to find out the power of 10, we count and see how many digits we move the decimal. 1, 2, 3, 4, 5. And since I'm moving to the left, this would be a +5. So the answer is B. The other way of looking at it is that the original number 353000 is a very big number, but you're moving the decimal right after 3, you're making it smaller. In order to compensate for that, the power of 10 has to be a +5. So let's look at measurements. So as scientists, as chemists, we will be doing lots and lots of measurements during the lab. Now, one thing to keep in mind is that each measurement has two components to it, a numerical value and also a unit of measurement. So any measurements done has to have a unit next to it. Without a unit, it's not a measurement. Now, an important aspect of measurements is the uncertainty in our measurement. To do measurements, we need instruments, and each instrument has some degree of an uncertainty that exists in that instrument. That uncertainty is the last digit of the measurement. So in order to see what the uncertainty of measurement is for each instrument, we need to investigate and look at the marking on each instrument very, very carefully. For example, here we have the picture of this thermometer here, and if you look at the marking, we see the marking for the one, so 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So I see the markings for the ones, 21, 22, 23, so on and so forth until 30. So if our goal is to read the level of thermometer of the alcohol here, so I can tell for sure that the level of alcohol is at 21. Why can I tell that it is for sure at 21? Because there is marking for the 21. Now, the question is that, does this level seems to be right on 21 to me, or does it seem to be a little bit over or under? Now, to me, it doesn't seem that it is exactly on the 21 marking. I think it's a little bit over. How much over? I can't really tell exactly how much over because I don't see any marking on the thermometer for this. So I'm just gonna guess, and I said, to me, it seems like it's 0.2 over. So I report the temperature here as 21.2 degrees Celsius. Now, to somebody else, if they do the reading, they may say that the temperature is 21.3, or someone might see this exactly at 21 degrees Celsius. Now, what's common in between all these measurements is the certain part of our measurement. The 21 is common in all three measurements. And it's common because we have marking on the thermometer, so we can read for sure that it's 21. The difference between these measurements is at the decimal point, the first decimal point, and it is totally okay because we're guessing this first decimal point. The reason we're guessing is because there is no marking on the thermometer. So in our measurement, this becomes the certain part of our measurement, and this becomes the uncertainty of our measurement. So what that also means is that any measurement done with this particular thermometer should be read to 1 decimal point. So for each instrument, we look at the marking on the instrument and see exactly what we can read, and you always guess 1 extra digit. So again, by convention, measurement typically includes all certain digits plus 1 digit that is estimated. So because of this level of uncertainty in any measurement, we express the measurement by a limited number of digits. These digits are called significant figures. So we're going to look at an example to see how the level of uncertainty can be different among measurements and different instruments. Here you see a picture of 2 different thermometers here. So thermometer 1, we look at the marking, and if you look at the marking, each one of these is to the 1, so 20, 21, 22. So to do the reading, I look at the level here. It's 22. I can tell for sure that it's at 22. So 22 becomes the certain part of my measurement. And then I think it's exactly on 22. So I'm gonna guess that it's 22.0. So I did the measurement 22 and I estimated or guessed 1 extra digit. Now, if you look at this other thermometer here, so the markings are a little different here because we see the marking for the 10th on this thermometer. So to do the reading, we know that it's for sure 22.1. So this is the certain part of our measurement, and we always guess 1 extra digit. So I'm just going to assume that it's 1 over 22.1. So any measurement done with this thermometer has to read to 2 decimal points. So it's very important before you do any measurement, you look at the marking and see how many digits you can read based on the marking on the instrument, and keep in mind that you always guess 1 extra digits. Now, because all measurements involve uncertainty, we must be careful to use the correct number of significant figures in calculations. Remember that the precision of a measurement, which depends on the instrument used to make the measurement, must be preserved. So not only when recording the measurement, but also when performing calculations that use the measurement. We as scientists, we can accomplish the preservation of this precision by using significant figures. In any reported measurement, the non-place holding digits, those that are not simply marking the decimal place, are called significant figures. And keep in mind that the greater the number of significant figures, the greater the certainty of the measurement. Now, in order to determine the number of significant figures in a number, there are some rules that we need to learn. So, the rules for counting significant figures, you need to memorize them. You'll be asked to just count the number of significant figures. So the rules, you need to memorize them. So rule number 1 is that all non-zero digits are significant. Some numbers have an infinite number of significant figures, whole numbers. So if you're counting, or if you're using a constant number as conversion factor, that's going to have infinite number of significant figures. Now, if in the number given to you there are zeros, 2 ways we can approach the zero. We have zeros that count as significant and zeros that do not count as significant. So you count 0 as significant if it comes in between 2 non-zero digits. For example, here, 75.04, it is a number that includes a 0. Now the question is that what type of a 0? It's a 0 that comes in between 2 non-zero digits, so you count this as significant figures. So this has 4 significant figures. You would also count zeros as significant if it's at the end of a number and that number includes a decimal. So for example, 32.410 is a number that includes a 0. Now the question is that what type of a 0? It's the 0 that comes at the end and there is a decimal in the number. So this counts as significant. So we have 1, 2, 3, 4, 5 significant figures for this number. Now 0 is not always counted as significant. So there are a couple of ways when we don't count 0 as significant. First situation is that if 0 comes before the first non-zero digit, it's not going to count as significant figures. For example, here the number 0.00321, it's a number that includes 0, but these 2 zeros come before the first non-zero digit, which is 3, so they don't count as significant. This number has only 3 significant figures. We won't count 0 as significant also if it comes at the end of a number and then there is no decimal. So for example, here 6,920, it's a number that includes a 0. Now what type of a 0? It's a 0 that comes at the end of the number and there is no decimal, so this doesn't count as significant. So this number only has 3 significant figures. Now let's do a couple of practice problems. We want to determine the number of significant figures for each one of these measurements. So 3.2, it's a number that doesn't include 0, so everything counts as significant. This has 2 significant figures. 25.0, it's a number that includes a zero. What type of a zero? Zero that comes at the end of a number and there is a decimal. So this has 3 significant figures. 103 people. It's a number that includes zero, and that zero comes in between two non-zero digits. Now the trick here is that 103 people represents counting the number of people. Remember, when we count, it's always infinite number of significant figure. So this is considered an exact number, and it has infinite number of significant figures. So again, why does this have infinite number of significant figures? Because if we pay attention to the unit here, we're counting people. And remember that when you count, you always end up with exact numbers, and counting means infinite number of significant figures. We look into significant figures if we're doing measurements, not counting. Now last one, 0.003 kilometers. So since we're measuring, we're gonna look into the significant figures. It is a number that includes zero, and those zeros come before the first non-zero digit. So this will only have one significant figure. Now, before we look at significant figures in calculations, we're gonna review the rules for rounding off numbers, because oftentimes in our calculations, in order to maintain a correct number of significant figures, we would need to round our numbers, either round up or round down. Now the rule is that when you're trying to round, if the number that you're rounding to, you look at the digit that comes right after that number, and if that digit is less than 5, you don't need to round. The number doesn't change, the last digit doesn't change. But if the digit that comes right after the number we're rounding to is more than 5 or more, you're going to round one digit up. So let's look at a couple of examples here. So for example, 79.137, you want to round this to 4 significant figures. 4 significant figures, meaning that you want to keep 7, 9, 1, and 3. Now the question is on the 3. Do I keep it as is, or do I round it up? So in order to answer that question, you look at the digit that comes right after 3, which is 7. 7 is more than 5. It means that you need to round this up. So this number rounded to 4 significant figures is going to be 79.14. Now this one, rounding this to 3 significant figures, so I'm going to keep 4, 3, and 4, so 0.43. Now the question is on the 4. The digit that comes right after 4 is 5, and our rule is that 5 and more, we're going to round one digit up. So this is going to be 0.0435. Next one, to 3 significant figures, meaning that I'm just going to keep 1, 3, and 6. The digit that comes right after 6 is 2. It's less than 5, so no change is needed. This other example, count this to 2 significant figures. We're going to keep 1 and 7. Now, since the digit that comes right after 7 is 9, we need to round one digit up, so it's going to be 0.18. Now let's look at significant figures in calculations. So when you use measured quantities in calculations, the results of the calculations must reflect the precision of the measured quantities. meaning that you should not lose or gain precisions during mathematical operations. So let's look at the rules that will help us keep the correct number of significant figures and precisions in our calculations. So if the calculations involve multiplication and division, the rule is that you count the significant figures for each number, and then your result should have the same number of significant figures as the number with the fewest number of significant figures. For example, here we're multiplying 79.2 by 1.1. So since it's multiplication, I'm going to count the number of significant figures. So this has 3 significant figures. This has 2 significant figures. And again, since it's multiplication, you want your answer to have only 2 significant figures. So you're going to keep only 8 and 7. And since the digit after 7 is 1, you just keep it as 87. So here we want to round the following calculations to the correct number of significant figures. So this calculation involves multiplication and division. So you're multiplying 12.18 by 5.2 and you're dividing that by 13. So let's do the calculation. So the answer we get from the calculator is 4.872. Now, since these calculations involve multiplication and division, we want to look at the number of significant figures to see how many significant figures our answer should have. So this has 4 significant figures. This has 2 significant figures. And this also have 2 significant figures, meaning that our answer should have only 2 significant figures too. So I'm going to keep 4 and 8. Now, since the digit that comes right after 8 is 7, which is more than 5, you're going to round this to 4.9. Now, the rule for addition and subtraction is different. So for addition and subtraction, the number of significant figures is not important. What's important is the number of decimal points. So you're going to look at the number of decimal points. So this has 2 decimal points. 79 has 0 decimal point, and this number has only 1 decimal point. So the rule is that your answer should have the same number of decimal points as the number with the fewest number of decimal points. So now in between these numbers, 79 has no decimal point, meaning that your answer should have no decimal point. So you add up 136.23 plus 79 plus 31.7. With your calculators, you're gonna get 246.93. Now you want to report your answer with no decimal point, meaning that you want to keep 2, 4, and 6, but you're gonna have to round this number to 247. So let's look at another example. So you want to subtract 13 from 142.57. Now if you do this with your calculator, you're gonna get 129.57. Now in terms of significant figure, this has 2 decimal points. This has only 1 decimal point. So we want our answer to have only 1 decimal point. So your answer is going to be 129.6.